Hello everyone, my name is Ashutosh Kumar Verma. Today I am going to talk on combined first principle and classical modeling of HPN water interface, how surface roughness and defect modulate wettability and friction. Let's first talk about introduction to solid liquid interface. So there are two properties. One is the contact angle and another one is the slip length. That is very important at solid liquid interface. So wettability is quantified by contact angle. When contact angle is greater than 90 degrees, the surface is called to be hydrophobic, and then contact angle is less than 90 degrees, the surface is called to be hydrophilic. No slip condition is valid at microscopic level. When we go below at nanoscale, then no slip condition is no longer valid. So when we linearly extrapolate the velocity profile at the distance at which velocity profile is going to vanish, that is called slip length. Two-dimensional material are ultra-thin nanomaterial which has unique properties such as high surface to volume ratio, high mechanical strength, and adjustable to chemical functionality. And 2D material has various applications. One of the important applications are water desalination process. So in water desalination process, this is a membrane that is made of HVN, and the water will pass through this HVN membrane from feed side to permeate side, and salt will be retained in feed side. Another important application is nanofluidics. In nanofluidics, liquid is passed through nanotube, and the property of liquid can be studied at nanoscale. Another one is osmotic energy harvesting. Here also this membrane is made of 2D material. Researchers are investigating the properties such as wettability, mechanical strength, friction of 2D materials. In the real world, 2D materials may contain defects such as vacancy defects. The effect of defect on the wettability and friction of HVN surface is recently gaining attention. So recently, Seal and Govind Rajan et al. Are reported friction coefficient on defective HVN, and also Verma et al. Reported water contact angle on defective HVN. So let's talk about system description. So here we have considered 6 topology. So in first case, you can see one V atom is missing. In second one, N atom missing, and similarly Bn, B2, and B3 N atom are missing. And this is an exposed edge. So these defects are observed experimentally under TEM imaging. And here this is our system where we have used 4 HVN layer, in which 3 are pristine and topmost one is defective one, and about 20 angstrom of water slab. And in this figure, you can see there are 4 pristine HVN and one is exposed edge. Now I'm going to talk about the concentration we have considered. So we have considered 2 different concentration. One we call higher concentration, one is lower concentration. So these 2 are for vacancy defect and these 2 are for exposed edge. So for vacancy defect, the concentration is defined in per unit area of the sheet, and for the exposed edge, the concentration is defined in total exposed length per unit area of the sheet. Young-Dupre equation relate the contact angle and surface tension using this equation. Work of adhesion equal to surface tension into 1 plus cos theta. So work of adhesion can be computed using free energy perturbation method. So in free energy perturbation method, what happening? We can remove water from the HVN surface, and computationally we can do that by making total interaction 1 to 0 with the help of soft core potential. Surface tension can be computed using this equation. Surface tension equal to L normal upon 2 into normal pressure tension minus tangential pressure tensor. And the slip length can be computed using this equation. Slip length equal to viscosity by friction coefficient. And friction coefficient can be computed using their force autocorrelation. So friction coefficient equal to limit t tends to infinity 1 over 2a kVt integration of force autocorrelation. Here A is the area of the sheet, kV is the Boltzmann constant, and T is the absolute temperature. Now next going to talk about modeling details. So we employed molecular dynamic simulation using LAMMPS, and we have used Govind Rajan et al. Force field and canonical ensemble Noje-Hoover thermostat at room temperature. And we also employed density functional theory using CP2K to compute partial charges. So to compute partial charges, we used DDAP scheme proposed by Bloch. Here you can see the bulk charges on pristine layer for B atom are 0.907 E and for nitrogen minus 0.907 E. When here in this figure, this is a HVN surface where one B atom is missing. Once B atom is missing, the partial charges on each atom are going to redistribute in a such a way that net charge will become equal to 0. So we computed work of addition on two different concentration, and this is we call a higher concentration. So here you can see this black one is for bulk HVN and this blue is for monolayer HVN. So in both cases the trend are similar. So in case of exposed edge, we got higher work of addition and compared to the pristine one. And this red line show twice of the surface tension at which contact angle become 0. And similarly, also we have computed work of addition for lower concentration. So here we can see that the work of addition for vacancy defects are insignificant with the vacancy defect, and this is because of the charge on each V and N atom are closer to their bulk. And also we computed water contact angle using Young-Dupré equation. So this first figure here is showing for higher concentration. So here we got lowest contact angle for exposed edge and highest for B3N. So this red line shows experimental value of 66 degree. And similarly, we have also computed water contact angle for lower concentration. So here with the exposed edge, we got 63.4 degree for bulk HVN and 68 degree for the monolayer HVN. That is very close to the experimental value. And here one more thing, that the effect of the effect are negligible in the case of lower concentration. So to understand the role of electrostatic interaction, we should consider both short range and long range interaction. So for long range interaction, we need to perturb the charges, but due to defect, the charge on each B and N atom are different. So we cannot perturb the charge. So instead of perturbing charges, what we can do, we can scale the short range interaction with the higher electrostatic cutoff. So here you can see for B vacancy and pristine case, the contact angle is not changing with the electrostatic cutoff. But in case of exposed edge, the contact angle is changes with the electrostatic cutoff. This figure show the contact angle. So here we have considered one van der Waals interaction only, and one case van der Waals plus electrostatic interaction. So first let's talk about pristine case. So in pristine case, we can see the contact angle is around 85 degree with van der Waals interaction. When we also consider electrostatic interaction, then contact angle come further down to 82.8 degree. And when we talk about boron vacancy, then the contact angle with van der Waals plus electrostatic, the contact angle become around 78 degree. So the electrostatic interaction play very important role in defective HVN. Apart from wettability, we also computed friction coefficient and water slip length. The experimental value of water slip length is 1 nanometer, and first time we have computed water slip length of 1.8 nanometer with monolayer roughness. The monolayer roughness is very important in explaining the interfacial property of HVN. So here you can see that we have computed friction coefficient over 3 different configuration and also slip length over 3 different configurations. So first one is the pristine. So for pristine, we got 1.7 into 10 to the power 5 Newton second per meter cube. And for exposed edge, for higher concentration, we got 7.2 into 10 to the power 5 Newton second per meter cube. And for lower concentration, 3.3 into 10 to the power 5 Newton second per meter cube. And using this formula, we got slip length. So this is a viscosity 1.32 millipascal second for T4P ice water model. And using this formula, we got slip length of 7.7 nanometer for pristine case, and for exposed edge with higher concentration 1.8 nanometer. That is a very close to the experimental value of 1 nanometer. And for lower concentration of exposed edge, we got 4 nanometer of water slip length. Now I am concluding my talk, and there are 3 major conclusions of this work. So first one is the the simulated water contact angle of 63.4 degrees is very close to the experimental value of 66 degree. And also the effect of defect are negligible at lower concentration. Second one is the electrostatic interaction between water and HPN depend on defect type. And third one is the estimate of 1.8 nanometer slip length, that is very close to the experimental value of 1 nanometer. I would like to say thanks to Professor Anand Gomirajan for his guidance, and also I would like to thanks to my group lab mate for their suggestion, and also I would like to thanks to National Supercomputer Mission and Supercomputer Education and Research Center for providing computational details. Thank you.
So I have maybe a clarification. So in the plots with the defects that you showed, so why did you choose those particular? Because those particular defects, is it because those are the ones that people see in experiments?
Sorry.
So there are different kinds of defects, right? B, N, and then
This one.
Yeah, this one, for example.
Yeah.
So these are the most common types of defects that people see in experiments?
Yeah, these defects are shown in using experimentally using TM imaging. That's why we have considered all the defects.
Okay, and the second question is, somewhere you had this, like you have a red line here.
Yeah, red line. This is the value at twice of the surface tension. So we also computed surface tension, and that was 73.5 millijoule per meter square. If you are going to take twice of that, so at here using a Young-Dupré equation, you will get contact angle equal to 0.
Right. No, somewhere it meant I think experiments or something, right? I maybe missed the slide number.
Experimental.
Yeah.
That is for contact angle.
Right. So here, do we expect like it in a sample, experimental sample? Is it a combination of all such things? What is that number corresponding to? Like all such defects one would expect in the experiment, right?
No, this is for only for representing experimental value.
Yeah. So can one understand like which defect probably edge is contributing the most, or is it not true? I mean, how to reconcile, like you have different kinds of defects?
Yeah. Okay. So here you can see like we are comparing with the experimental value. So in case of vacancy defect, this is for higher concentration. So we are not getting close to the experimental value. And also in case of exposed edge, we are getting very far away from experimental value. But when we are considering lower concentration, in that case, with the help of monolayer roughness, we are getting the contact angle that is very close to the experimental value.
So one would then conclude that that is more relevant.
Yes.
Okay. Yeah. Shobna.
Can you say a little bit more about why the wettability of BN is important? What applications can it have?
Sorry, can you repeat?
Why are you interested in this problem? What are you going to use it for?
Okay, so my problem is based on actually we are studying the wettability and frictional. So nowadays researchers are what they are doing. They are using 2D material as a membrane, and one of them application are water desalination. So water is going to pass through nanopore. So basically they are not considering the how the flow of water is going to vary with the, yeah, that is also possible. So if you, so here I have considered bulk water on HUN surface.
All right. Any further questions? Okay. If not, let's thank the speaker again.